So we talked about the appearance of the position versus time graph. The initial position and the final position are by the detector. So that's why A and C are located there. B is as far away from the detector as possible. And then right at the end of the period, yep. Stew on that a while. Right at the end of the period, we were talking about the slope here at B as being 0. So, if you need this somewhere just as a reminder how to translate slope, what does it look like if there's a negative slope? What does it look like if there's a positive slope? Or what does it look like if there's no slope at all? So 0 slope or horizontal. And at B, yeah, it's horizontal, it's flat. So that's how I know on the velocity graph that I'm going to have a velocity of 0 at that time. But what should the slope on the velocity time graph look like before that? I'm sorry, not what should the slope. What should the velocity look like prior to that? And the key to that is looking at the slope at A. Or what should the velocity look like after this point where the velocity is 0? The key to that is looking at the slope at C. So ponder that quick on the pear deck. And I'll see if you got any changes there. So again, you're going in, you're looking at your velocity time graph, being mindful of those things. Right now, when I look at it, we've got the same position versus time graph. We've discussed that. We are all over the map on the velocity versus time graph. So, again, what I'm asking you to do is take a look at the position time graph and break that into chunks. You might even put in kind of like a little intermediate chunk here. Call that A2, okay? Or a little intermediate chunk here, B2. When you compare the slope at that time to what the slope is going to be at C or what the slope was at B, what is that telling you about the velocity value? We're in this thing. All right, so here are kind of like the 4 or 5, I guess, main types of things I'm seeing. This kind of thing, that kind of thing, that kind of thing, that kind of thing, or that kind of thing, okay? I think it might be best if we just went into the graph and tried to capture it here and see what we end up with. Meter stick. So there's the position versus time graph that we're expecting. Okay, it's got that appearance. If you look at the velocity versus time graph during that same time, I don't need the numbers to go quite this high. So when we're here, this starts out really positive because this starts out with a really positive slope. But over time, the velocity is less positive. Here it's half as much. The slope is less steep at that time. And again, in the middle, you've got a velocity of 0 because at the very tippity top there, you've got a slope of 0. So it's all about taking that curved graph and kind of breaking it into the different shapes, or different line segments, I should say. What are you doing? Come on, give me the new. There we go. So I want to take that curve and at various times, the love of Pete. There we go. Take that curve and again, think about what is the slope of the curve like at various points. And these little green segments that I've drawn there, they all slope up, but it's getting less and less steep. And then at the very top, it's going to be flat, and that coincides with on here where the velocity is 0. And then on the way back down, these slopes are all negative, and it's getting steeper, and that coincides with the velocity value itself becoming increasingly negative, okay? So here's our velocity versus time graph. And again, we're working off of these understandings that velocity is the slope. Oh, come on position versus time graph. Boy, this pen is struggling today. There we go. Acceleration. What is your deal? Is the slope on the velocity versus time graph. So let's pop back over into the Pear Deck here. And can you write a few words for me about the slope that you see on that velocity versus time graph? What are some words you would use to describe that slope? And so again, I'm just asking for descriptions of the slope of this graph. So if you're looking at it, I can hold the meter stick up like that. And notice how that part of the graph lines up with the meter stick, that part of the graph lines up with the meter stick as well. So I'm seeing things like negative, constant negative, slope of the velocity versus time graph is constant negative, okay? Seems like we're in pretty good agreement on the appearance of that slope. So now what I'm asking you to do is apply that understanding along with this physics thing that acceleration is the slope on the velocity versus time graph. So now if you go into your acceleration graph, I'll back you up. Maybe I will. Now go into that acceleration graph and draw an acceleration graph that fits the description you just gave of the slope on the velocity versus time graph. Your acceleration value should fit with the description you gave of the slope on the velocity versus time graph. And yeah, you can fix your velocity graphs while you're at it. Some folks are drawing some things that kind of look like the full breadth of what's on the screen. Again, I really just need you to be thinking about the graph from point A here to point C down here. This is B in the middle. So you don't really need to draw anything before A or anything after C. What should our acceleration graph look like? Again, our description of the slope on this thing was that it is constant and negative. And again, if I draw a little segment to go along with this here, kind of close to A, anywhere that I drag that along this graph, it fits. Even if I go down here into the portion of the graph where the velocity is negative, that line still has that same slope. Even if I go here to B and I just drop it right in the middle there, that's the same slope that I had here, that's the same slope that I have here. At no point in time is it going to have any other value than that constant negative value. So when I look at your pear deck over here, there isn't this kind of jump that's happening. The slope after the velocity is zero is just as negative as it was before the velocity is zero. Okay. It doesn't drop out ever. So that's kind of a couple of, like, this type of thing isn't happening either. Okay, where you have a velocity that, or sorry, an acceleration that all of a sudden at one point in time changes to zero. It's the same value the whole way through. We can just go look at it over here on the actual graph. It's, oh gosh, the heck. So over here you've got the poosh, and over here you've got where it stops. But if you look at this, that's a pretty constant value through that whole thing. Okay, it's got a value of roughly -1 meter per second squared. And that should jive with the slope on the velocity versus time graph. If you look at it on this velocity versus time graph, starts out with the velocity of +1, ends up with a velocity of about -1. Wonder if I can get a slightly better version of this graph. About as good as it gets. You can see here it ends up. Yeah, that's about perfect. Let me grab a picture of this quick. So if we were to go in and try to calculate the slope value here, numerically, we start off with a, come on, man. Give me the pen. So we start off here with a velocity of 1 meter per second, and that's at time 1 second. We end up with a velocity of negative 1 meter per second, and that's at 3 seconds here. So if you calculate the slope, you're going to have negative 1 meter per second minus 1 meter per second. And I'm going to divide that by 3 seconds minus 1 second. Negative 1 minus 1, who's got a calculator? Nobody? That's negative 2 meters per second. 3 seconds minus 1 second, that's 2 seconds. So if I work this math out here, I get negative 1 meter per second. And that agrees with what I see up here for my acceleration value. This is basically going across at a steady negative 1 meter per second. Here's a question for you and your neighbor. What is the takeaway from that blue triangle and this green triangle? Okay, take a moment. You bet. It's kind of tough to see what's blue and what's green there. You show off the lights. So if you look at this, what are the takeaways from that blue triangle and that green triangle? Okay, take a moment and chat about that with your neighbor. We talked about the slope, but what about the area there? What is that telling you? And then once you've had a chance to chat about it with your neighbor, go ahead and clear that up. What is the significance of the area limit to count about this? All right, let's see what our friends had to say about those areas. So they have the same area, negative versus positive areas. The areas in the two triangles is equal to the total displacement of the object. They are the same but flipped negatively and positively. Two areas are equal because one is positive and the other is negative. this thing frozen. Come on. There we go. Two areas are equal, and because one is positive and the other is negative, the car ends in the same place it started. There's no net displacement. So yeah, I guess that's kind of the thing I want you to think about here. If we total these up, if you add this blue triangle to this green triangle, what are you going to get for the total area? And I don't think, bummer, it didn't go as one solid thing, but you can pretty much see, maybe if I outline it. That those are going to kind of bookend, yeah? If I set it up top. The one is as positive as the other is negative. So the total area here equals 0 meters. Is that how you short up because? Because the cart has the same initial and final positions. Okay, so that's the interpretation of that area. Now I'd like you to think about the interpretation of this area. What is represented by this rectangle here? You're looking at an acceleration versus time graph, okay? So I'll throw a new question on there for you for this. What is this? Run that by your neighbor first. When you do a little dimensional analysis, think about the graph itself and say, what is the significance of that rectangle? So I'm seeing some references to distance, but think about this as a rectangle. This side here, okay, that's -1 meter per second squared. And then this here, the base of this thing, basically it's running from 1 to 3. So the base of this rectangle is 2 seconds. So if you're calculating the area, you're going to have 2 seconds times -1 meter per second squared, or I think it's maybe handier to write that as meters per second. Mathematically, that's going to be -2. And then dimensionally, you've got seconds times meters per second over seconds, okay? And that's going to leave you with meters per second. What is the significance of -2 meters per second? If you look at the velocity graph, it never goes -2 meters per second. What is the meaning of that? Run that by your neighbor quick. Yeah, somebody wrote average speed. Is that the average speed? What is the significance of -2 meters per second of this graph? So this is a kind of a callback to the CDPM. This understanding of the area between the velocity versus time graph and the x-axis represents the change in position. On this graph, we didn't calculate it, but we talked about it. That blue triangle and that green triangle, this is positive, this is negative. If you add them together, you're going to get a total of 0. And that relates to the change in position. So what I'm asking you to think about here is the significance of the area of this acceleration versus time graph. Whoa, buddy. The area of this acceleration versus time graph being negative 2 meters per second. What is negative 2 meters per second to this graph? And that's what I'd like you to type into the Pear Deck, okay? A couple people are typing in that it might be the slope on this graph, but keep in mind we calculated the slope. The slope here is negative 1 meter per second per second. So it's got a different number value, it's got a different unit too. Okay? This thing doesn't come out as acceleration units. This thing comes out as meters per second. Where do you see negative 2 meters per second here? So we're seeing things like the change in velocity from initial to the final, the time it took travel going up and down the ramp, average speed, net change in velocity over the entire graph, the change in speed. Can you see how that kind of relates to our understanding here? That the velocity graph, that area represents the change in position, okay? This acceleration graph, that's going to represent that negative 2 meters per second. Thank you. That's the change in velocity. It starts out with a velocity of 1 meter per second. It ends up with a final velocity of negative 1 meter per second. So that's this bit right here, right? We calculated the change in velocity and got that to be negative 2. That's what this area tells us. The area between the acceleration versus time graph and x-axis represents, buddy, the change in velocity. So we've got the slopes telling us something as we go in one direction on this graph stack, and the area is telling us something else. So if I got a graph of position versus time, the slope tells me about the velocity versus time graph. The area on the velocity versus time graph tells me about the position versus time graph. And now similarly, you've got the slope on the velocity versus time graph telling you about the acceleration versus time. The area on that acceleration versus time graph is telling you about the change in velocity. So those are kind of a couple big relationships here. All right. Let me get this passed out to you then. This is where we're going next. A little bit of practice with some of these ideas. Ooh, I take that back. One other thing we didn't talk about yet, and that's the motion maps. So we pop back over to the OneNote. It's on here. Let's see. Yeah, so if you've got this this worksheet, cart going down the ramp. The motion map is going to look just like your tape. The dots are going to get farther apart because this thing's getting faster. And so the arrows on here are not going to be the same length. They're getting longer. So those are the velocity arrows. And then we're going to add something else in here that we didn't have to do before. And those are the change in velocity arrows. Basically, I want to show what am I adding to this arrow to get the next one. And if I add those two things together, that gives me this arrow. Okay, so what I'm basically going to do here is if I take, come on, there we go. If I take that and, buddy, and that, and I add those two things together, right? That's how I get that arrow. So you don't necessarily have to draw it in a separate color, but that's what the hollow dot arrow represents. It's the change in velocity. And so then for this guy, I'm going to draw it like that. For you, I'm going to draw it like that. For you, I'm going to draw it like that. These all have the same length because, again, the velocities are changing by the same amount every second. So if I take this arrow over here, this is the thing that I'm adding. This is the thing that I'm adding to it to get that next velocity arrow. That's why it's a change of velocity arrow. There we go. Aye. So this is what it looks like when it's getting faster. So if you got this worksheet somewhere, go ahead and add in the motion map on here. And then think about how that would look for this thing. This thing's slowing down. I don't want to do red. This thing's getting slower. So it's going to start out with a bigger velocity. But then over time, I think I can draw this better than that. Over time, those arrows are getting smaller, okay? So think about this in terms of arrow math. I have this arrow. What do I add to it to get this arrow right here? And if you kind of take them side by side, what do I add to that to get a shorter arrow? Well, you can imagine if this is, let's say, 8 meters per second, this is 6 meters per second, this is 4 meters per second, 2 meters per second, and this last one is 0 meters per second. What am I going to add to 6? Or sorry, what am I going to add to 8 to get 6? And that's going to be negative 2 meters per second. Eight plus negative 2, that's how I get 6. 6 plus negative 2, well, that's all going to come out separate. That's real handy. 6 plus negative 2, that's how I'm going to get 4. 4 plus negative 2, that's how I'm going to get 2. And then finally 2 plus negative 2, that's how I'm going to get 0. So the hollow dot arrows for this part of it They point the other direction. Really? What is going on here? So those are all kind of pointing like that. All right, so I'll leave that to you to add in the motion maps with the hollow dot arrows to represent the change in velocity on that worksheet. And then this is where we're heading with this thing next. So this worksheet, I think we already talked about the name of this model. So constant acceleration particle model. Or CAPM. You've got a velocity versus time graph here. It starts out with a velocity of 6 meters per second. And then by the end of this time here, you've got a velocity of 0 meters per second. So written description of the motion. Can I go in and change text on these things? I cannot. That's sad. There's an error we need to correct here. And a lot of textbooks get this wrong. Those aren't acceleration arrows. They're change in velocity arrows. The units on them are meters per second. And then you got to determine the displacement here for a period of time and for a different period of time. Keep in mind, when you see that word displacement, that's just a fancy way of saying change in position. All right, so that's all the stuff you're having right there. Go ahead and work on that with your neighbors. Yo.